All right, everyone. I want you to imagine something for a second. Imagine if one single, mistaken command could lose millions of our members' watch histories. Permanently. Just gone. Now, that's not some hypothetical what if. It's a very real threat that we face every single day. So today, I want to talk about the invisible hero that stands between us and that kind of catastrophe. Our write-ahead log platform. It's the silent guardian that ensures every click, every play, and every single interaction on Netflix is safe. And it's the foundation for how we're able to innovate at a global scale.
So, how did we build this digital fortress? Well, here's our plan. We're going to start by looking at the real-world data catastrophes that were keeping our engineers up at night. Then, we'll cover the digital safety net, the core concepts that actually inspired our solution. From there, I'll walk you through the resilient platform we built, and we'll dive into some really cool examples of the wall in action. And finally, we'll wrap up with the key lessons from scale that are really shaping how we think about engineering at Netflix going forward.
To really get why we invested so much in building this platform, you first need to understand the precarious environment we operate in. When you're serving hundreds of millions of people all over the world, even a tiny problem can escalate into a catastrophic failure in the blink of an eye. Look, this isn't just about a technical glitch. This is about the trust our members place in us. Can you imagine having to tell millions of people that their watch history, their profiles, their carefully curated recommendations are just gone? Forever? That's the exact scenario this quote from our own tech blog is describing. We dodged a massive bullet that time, thanks to some truly heroic last-minute efforts. But it was a huge wake-up call. We knew we couldn't rely on luck. We had to engineer a system that makes this kind of failure basically impossible.
And it wasn't just one problem. It felt like we were fighting a hydra. You'd solve one issue and two more would pop up. We were dealing with everything from accidental data corruption to the nightmare of keeping different systems like our Cassandra databases and our Elasticsearch indexes perfectly in sync. We were struggling with how to update multiple database partitions at the same time and how to replicate data for our caches all over the globe. Our retry mechanisms were often custom-built and, frankly, unreliable. And get this, even a simple operation like deleting a bunch of data after a live event could create these massive request spikes that would cause our servers to just run out of memory. Each one of these challenges meant production incidents, countless engineering hours spent fighting, and a mountain of technical debt growing across the whole organization.
So, before we jump into our solution, we need to quickly touch on the two foundational technologies that make it all work. Now, these aren't new ideas. They're proven, industry-standard concepts. Think of them as our digital safety nets.
Okay, first up, the message queue. The best way to think about this is like a digital post office. When one part of our system needs to send info to another, it doesn't have to deliver it in person, right? It just drops the message in the mailbox. The post office then guarantees it'll get there, even if the recipient isn't home or is totally swamped with other mail. It's this simple idea that lets our incredibly complex systems talk to each other reliably, even when things get chaotic. The second concept is the write-ahead log, or WAL. Now, the principle behind this is what's really cool. It's like a meticulous accountant's ledger. Before any money actually gets moved between accounts, the accountant first writes down the intended transaction in their ledger. That way, if the power goes out or something crazy happens, that ledger is a perfect, indestructible record of exactly what was supposed to happen. Our WAL does the same thing, but for data. It's our ultimate source of truth, making sure that even if a server crashes right in the middle of an operation, we never ever lose a single transaction. So we didn't just grab these tools off the shelf and call it a day. No, we took these powerful concepts and built a really clever, flexible abstraction right on top of them. This platform approach meant we could solve all those different Hydra heads at once, instead of building a bunch of one-off solutions for every little problem.
And here's the crucial idea. We created one single, simple API called write-to-log. This API completely hides all the messy complexity of Kafka, SQS, durable storage, and all the tricky retry logic. Our goal was to make doing the right thing, building resilient, durable systems, the easy thing for every single developer at Netflix.
So what does this actually mean for our developers? It means a massive boost in productivity. Instead of spending weeks building these complex, error-prone data pipelines, they can now get guaranteed data delivery with just a single API call. They just tell our wall platform what they want to do using these simple parameters, and our platform handles the how. This frees them up to focus on what they do best, building amazing new features for our members and doing it faster than ever before.
And this slide really shows the power of the design.
We strictly separated the producers of messages, the ones sending them, from the consumers, the ones processing them. This is absolutely critical for resilience. If the system processing the data slows down, the system sending the data isn't affected at all. Our architecture is also pluggable. That means we can swap the underlying technologies, say from Kafka to SQS, with just a simple configuration change. That future-proofs the whole platform. And critically, every single setup automatically gets what's called a dead letter queue. So if a message repeatedly fails to process, it's not lost forever. It's safely set aside for an engineer to look at.
Okay, let's move on and see how this actually works in the real world. We like to think of these different configurations as personas, where our single wall system puts on different hats to solve very different kinds of problems for our engineering teams.
First up, the delayed queue persona. So, imagine a big live event just finished, and our system needs to delete a huge amount of temporary data all at once. As you can see on this chart, that creates this massive, dangerous spike in requests. That spike can totally overwhelm our databases and even interfere with real-time member traffic. Not good. So our solution is pretty elegant. We have the service write those delete requests not directly to the database, but to a wall namespace configured as a delayed queue. The wall system just accepts all of those requests instantly, but then it introduces a small random delay to each one. This completely transforms that dangerous traffic spike you saw into a gentle, manageable stream of requests over time. It protects our core databases and ensures the member experience is never impacted by our own background work.
Next up, let's talk about cross-region replication. A lot of our in-memory caching systems like EVCache are super fast precisely because they're simple. They don't have complex, built-in replication features. But we need that data to be available all over the world for performance and resilience. So we needed a generic way to make them globally consistent.
So the wall system basically becomes our replication engine. When an application writes to its local cache, say in the US, the client also sends that same write to a wall namespace. That namespace, using Kafka under the hood, publishes the change. Our wall consumer groups, which are running in Europe and Asia, are constantly listening. They immediately see that new message, they pick it up, and they apply the exact same write to their local caches. And just like that, we have a generic, reliable, cross-region replication system that any data store can use, without having to build this complicated logic itself. All right, finally, let's look at the most complex persona. This one solves one of the hardest problems in distributed systems. How do you guarantee that a set of related writes are atomic? And what that means is they either all succeed or they all fail together. You can never, ever leave the system in a partially updated, inconsistent state.
To solve this, we use a technique called a two-phase commit. You can think of it like a contract negotiation for data. So first, in steps 2 and 3, all the different parties involved agree on the terms of the deal, and they sign a sort of preliminary agreement. For us, this is like writing all the individual changes to our durable storage. Then, and this is the most important part, once everyone has agreed, they all sign the final contract at the exact same time. That's step 4, our completion marker. It's the single final go signal that the deal is done, and only then, in step 5, is that marker put on the queue. So, when our consumer system sees that final marker in step 6, it knows the contract is final. It can go back, reassemble all the preliminary parts, and execute the whole deal. This two-phase process guarantees that a really complex transaction either happens completely or not at all. No more data inconsistencies. So as you can see, we have one core platform that's solving 3 very different, very difficult distributed systems problems. For those crazy request bursts, we use the delayed queue persona, backed by SQS. For global consistency, we use the replication persona, backed by Kafka. And for those atomic all-or-nothing writes, we use the multi-table mutation persona, backed by Kafka, plus a durable key value store. This really demonstrates the power and the strategic value of having a well-designed, flexible platform. So what does this all mean for us as we move forward? Well, the story of the WOW platform isn't just about this one system. It's really about codifying a set of fundamental principles for how we design modern software here at Netflix. The crucial takeaways are these. First, a pluggable architecture is a superpower. It means we can adapt to new technologies without doing costly, risky rewrites. Second, leveraging existing, proven building blocks let us move way faster and deliver this platform with a smaller team. Third, that strict separation of concerns is what gives us the ability to scale and handle failure so gracefully. And finally, we were very intentional about our trade-offs. We chose durability, meaning the data is never lost, over immediate consistency. And in plain English, that means we decided it is far, far better for an update to be slightly delayed than for it to be lost forever.
That's a core principle that protects our members' data.
And we are not done yet. This same platform is now the foundation for our next set of high-leverage projects. We're already planning to use it to build secondary indexing on top of our key value stores, which is going to unlock a ton of new product features our developers have wanted for years. We'll also be using it to guarantee writes to completely different kinds of data stores at the same time, like, for example, writing to a primary database and a search index simultaneously, and ensuring they are always perfectly in sync.
So I'll leave you with this final thought. This type of invisible, resilient infrastructure, it's the bedrock of all modern digital services. It's not a flashy new feature that gets a press release, but it's the quiet, reliable foundation that prevents catastrophic failures and enables the very innovation that our members see and love every single day. It's the reason you can trust that when you hit save or you hit play, it just works.